You update a DNS record, refresh your browser, and nothing changes. You check your DNS panel and the new record is definitely there. But the old website is still showing up. What's happening? This is DNS propagation, and it confuses nearly every developer the first time they encounter it. The DNS system is designed for high performance through aggressive caching, and that caching is exactly what makes immediate DNS changes impossible. When you update a DNS record, you update it on your authoritative nameserver, one server, or a small cluster. But there are thousands of DNS resolvers around the world that have previously cached your old DNS record. They won't query your nameserver again until that cached record expires. The expiry time is controlled by the TTL, time to live value on the DNS record. A TTL of 3600 means resolvers can cache that record for 3600 seconds, 1 hour, before they're required to query again. A TTL of 86400 means 24 hours. The common misconception, DNS propagation, implies DNS records are actively pushed out to servers around the world. That's not how it works. DNS propagation is passive. Resolvers keep serving the cached version until their TTL expires, then they requery the authoritative server and get the new version. The good news, you have control over this. By setting low TTLs before plan changes and high TTLs after things are stable, you can minimize propagation time when you need to move fast. TTL is a number in seconds. It tells DNS resolvers how long they're allowed to cache a record before they must query the authoritative nameserver again. TTL of 300, resolvers cache this record for 5 minutes. Every 5 minutes, they requery for the latest value. Changes propagate to most resolvers within 5 to 10 minutes. TTL of 3600, resolvers cache for 1 hour. Changes take up to 1 hour to propagate. TTL of 86400, resolvers cache for 24 hours. Changes can take up to 24 hours to propagate worldwide. TTL doesn't guarantee propagation time, it's the maximum. If a resolver cached your record 10 minutes ago and the TTL is 3600, that resolver won't requery for another 3590 seconds. Another resolver that cached it 3590 seconds ago might requery in 10 seconds. The propagation time depends on when each resolver last cached the record. The trade-off, low TTL faster changes plus more queries to your nameserver. High TTL slower changes plus fewer queries, faster performance. For most DNS providers, there's a minimum TTL you can set, usually 1 second for providers like Cloudflare or 60 seconds for others. Default TTL values from major providers, Cloudflare defaults to auto, usually around 300. Route 53 defaults to 300. Many registrars default to 3600 or 86400. When you create a new record, no old record to expire TTL doesn't affect how quickly the new record becomes available, since there's nothing stale in caches. The first query for a new record goes straight to your authoritative server. Let's map out exactly what happens over time when you change a DNS record. Scenario, your record has TTL 3600. You change the IP from 1.2.3.4 to 5.6.7.8. Time 0, you make the change at your DNS provider. Your authoritative nameserver now returns 5.6.7.8. Time 0 to 3600, resolvers that have previously cached your record are still serving the old IP 1.2.3.4. They won't query your nameserver until their cache expires. Time varies. Resolvers whose cache is about to expire, or has already expired, start querying your nameserver and getting the new record 5.6.7.8. These resolvers now serve the new IP. The catch, even after you lower TTL to 60 seconds, resolvers that cached your record with the old TTL of 3600 will hold on to it for up to 3600 seconds. You need to change the TTL and wait for existing caches to expire before the lower TTL takes effect. This is the migration strategy paradox. If you lower TTL from 3600 to 60 to prepare for a migration, you need to wait 3600 seconds, the old TTL, before the lower TTL is widely cached. Then your changes will propagate quickly. Time plus old TTL, all resolvers have expired their caches and requeried. Everyone gets the new record. Propagation is complete. In practice, for popular domains visited frequently, propagation often completes in 15 to 30 minutes even with 3600 TTL, because resolvers requery more frequently for high-traffic records. For rarely visited domains, it can truly take the full TTL duration. The professional way to migrate servers with minimal DNS downtime. Step 1 to 48 hours before migration, lower your TTL. Change the record TTL from 3600 or 86400 to 60 seconds. Don't change the actual IP yet. Step 2. Wait out the old TTL. After you lower the TTL, you need to wait for the old high TTL caches to expire worldwide. If the old TTL was 3600, wait 3600 seconds 1 hour after the TTL change before proceeding. If it was 86,400, wait 24 hours. Why wait? Because resolvers cached the old TTL value along with the record. A resolver that saw TTL 86400 an hour ago will keep that cache for another 23 hours regardless of what your nameserver says now. Step 3. After waiting, now most resolvers have requeried and cached the new TTL of 60 seconds. Changes to the IP will propagate within 60 to 120 seconds. Step 4. Make your change, update the record to the new server IP. Step 5. Monitor, check propagation with dig at 8.8.8.8myap.com and what'smydns.net. Within 2 to 5 minutes, most resolvers should have the new IP. Step 6. After confirming new server works, wait a few hours to ensure no traffic is going to the old server, then decommission it. Step 7. Raise TTL back. After migration is complete, increase the TTL back to 3600 or higher for better performance. This strategy applies to any planned DNS change, server migration, DNS provider change, CDN addition. After making a DNS change, verify propagation with these tools. From the command line, dig myap.com, queries using your local resolver. This shows what your ISP or local network is seeing. Includes the TTL in the answer, which tells you how long the cached record has left. Dig at 8.8.8.8myap.com, queries Google's public DNS. Shows what Google's resolver sees. Useful because 8.8.8.8 is widely used and heavily cached. If Google has the new record, most users will soon too. Dig at 1.1.1.1myap.com, queries Cloudflare's public DNS. Another widely used resolver to check. Dig at 208.67.222.222myap.com, queries OpenDNS. Flush your local DNS cache, sudo systemd resolve flush caches on Linux, IP protocol configuration /flushes on Windows, sudo tskshutl flush cache on Mac OS. This clears your local cache so you see the latest record, not the cached one. Online tools, what'smydns.net, shows DNS resolution from locations worldwide. Enter your domain and select the record type. You'll see which locations have the new record and which still have the old one. Highly useful for monitoring propagation. dnchecker.org, similar to what'smydns.net. dnsspy.io, provides historical DNS records. Understanding the output, when different geographic locations show different answers, propagation is still in progress. Wait until all locations show the new record. With a 60-second TTL, this should take 5 to 10 minutes globally. The term DNS propagation creates a mental model of DNS records being actively pushed out across the internet. That model is wrong, and understanding why changes how you think about and debug DNS issues. The real model, DNS, is pull-based, not push-based. Your authoritative nameserver waits passively for queries. Resolvers query it when their cached records expire. There is no mechanism to push new records to resolvers immediately. DNS propagation delay is really just TTL expiry delay. The time you're waiting is for cached records to expire, not for records to propagate somewhere. What this means practically, if someone tells you to wait for DNS to propagate, they mean wait for existing caches to expire and resolvers to requery. If a record change isn't propagating after many hours and the TTL is low, the problem isn't propagation, it's that the old records are being served from caches that cached with a high TTL. If you need to speed things up for testing, use dig at 8.8.8.8 to bypass your local cache. If Google's resolver has the new record, your query to Google's DNS will get the new answer immediately. There is one genuinely slow part: NS record delegation changes. If you change nameservers at your registrar, the registrar's change needs to propagate to the root servers and TLD servers. This can take 24 to 48 hours because TLD nameserver TTLs are typically very high and are managed by the TLD operator, like VeriSignFor.com, not by you. If you're using Cloudflare, there are specific TTL behaviors to understand. Cloudflare minimum TTL. In Cloudflare's DNS panel, the minimum configurable TTL is 1 second for paid plans and around 60 seconds for free plans. If you select automatic TTL, Cloudflare uses 5 minutes, 300 seconds, for non-proxied records. Proxied records in TTL. When you enable the Cloudflare proxy, Orange Cloud, the TTL becomes irrelevant for external clients. Clients always connect to Cloudflare's edge servers, not your origin. Cloudflare serves its own cached response from its CDN edge. The TTL you set only affects how long Cloudflare itself caches the record internally. Cloudflare's cache purge. In the Cloudflare dashboard, you can purge the cache for proxied content. This forces Cloudflare's edge servers to refetch from your origin. This is different from DNS TTL, it's the CDN cache, not the DNS cache. For DNS-only records, GrayCloud TTL works normally. External resolvers query Cloudflare's nameservers and cache the response for the specified TTL. Cloudflare's edge network, because Cloudflare operates hundreds of edge nodes worldwide, when you update a DNS record in Cloudflare's panel, the update propagates to all Cloudflare edge nodes within seconds. External resolvers then have Cloudflare as a fast source. This is faster than traditional DNS providers. The practical effect: with Cloudflare, DNS changes are visible from Cloudflare's nameservers almost instantly after you save. What takes time is for external resolvers' caches to expire. There's another form of DNS caching that surprises developers: negative caching. This is caching of the fact that a record doesn't exist. When a DNS resolver queries for a record and gets next domain, no such domain, or an empty answer, it caches that negative response. For a configurable time, the negative TTL, defined in the SOA record, it serves the cached doesn't exist response without requerying. Real scenario: you create a new subdomain staging.myap.com. Someone queries for it before you added the DNS record and gets next domain. Their resolver caches that negative response. You then add the A record. They query again, but the resolver serves the cached next domain. This domain doesn't exist even though it now does exist. The fix: wait for the negative cache TTL to expire. The negative TTL is in your SOA record, typically 300 to 3600 seconds. After it expires, resolvers will requery and get the positive answer. How to check: dig staging.myap.com. If you get next domain with a low TTL, the negative cache will expire soon. Dig at 8.8.8.8 staging.myap.com. If Google's resolver returns next domain with a 5-minute TTL, you need to wait 5 minutes. Testing new records from your machine: flush your local DNS cache first, sudo systemd resolve flush caches, then dig to bypass the negative cache. Or query directly against the authoritative nameserver. Dig at ns1.yourprovider.com staging.myap.com. Negative caching is why testing with dig against specific resolvers is important when working with newly created DNS records. Practical TTL values based on the situation. For new records, just deploying for the first time, start with 300 seconds. There's no existing cache to worry about. You can adjust quickly if needed. For stable, production records, 3,600 to 86,400 seconds. This reduces DNS query load on your nameserver and gives faster resolution for users. Resolvers cache longer equals fewer lookups. Only change to lower TTL when you're planning changes. For records you change frequently, like records pointing to dynamic resources, 300 to 600 seconds. The overhead is acceptable for the flexibility. Before any planned server migration, lower to 60 seconds at least old TTL duration in advance. If current TTL is 3600, wait 3600 seconds after lowering before making the IP change. After a migration is confirmed stable, raise back to 3600. You no longer need rapid propagation and the lower TTL is just unnecessary overhead. TTL and server downtime: if your server goes down unexpectedly with a 86,400 TTL on your DNS, users who cached the record in the last 24 hours might keep trying the old IP for up to 24 hours. Low TTL is important for high availability scenarios, but high TTL is important for performance. Balance based on your uptime requirements. For critical production records that you never want accidentally cached incorrectly, 300 is a reasonable balance between performance and agility. High enough to reduce load, low enough that mistakes are fixable within 5 minutes. A scenario that tests understanding of the migration strategy. Your production A record for myap.com has a TTL of 86,400, 24 hours. You need to migrate to a new server tonight, and you want the migration to go smoothly with minimal downtime. You're starting your planning process right now. What's the correct sequence? Option A: lower the TTL to 60 right now, wait 5 minutes, then update the IP and you'll be done. This is wrong. You can't wait just 5 minutes. The old TTL of 86,400 means resolvers have cached the record for up to 24 hours. You need to wait the full old TTL duration after lowering, otherwise resolvers that cache the old record with the 86400 TTL won't requery for up to another 24 hours. Option B: lower the TTL to 60 right now, wait 24 hours, then update the IP tonight. This is the correct approach. After you lower the TTL, you wait for the old 86,400 second caches to expire. That takes up to 24 hours. After 24 hours, most resolvers have requeried and cached the new 60-second TTL. Now your IP change will propagate globally within 2 to 5 minutes. Option C, update the IP directly tonight and accept some downtime. Possible, but you'll have users hitting the old server for up to 24 hours. Not minimal downtime. Option D, contact your DNS provider to push the change globally immediately. DNS doesn't have a push mechanism. There's no way to force resolvers to expire their caches. The answer is B. The professional migration pattern: lower TTL early, wait for old TTL to expire, then make the change for fast propagation.